We're looking at the mole. And we've looked a little bit at the mole. I've talked briefly about it. But basically we want to know, what is a mole? Is it this thing? No, well, it's a mole, but it's the wrong kind of mole. We're talking about the chemistry mole, the mole that we use as chemists. So the question is exactly, what is a mole? Well, very simply, as we talk about moles, we find out that a mole is just a quantity. Again, it's not that mole. Like a dozen is 12 things, a pair is 2 things, and so on and so forth. A mole is just a number. It's a quantity. And a mole happens to be 6.02 times 10 to the 23rd things, a really, really, really big number. And that number, 6.02 times 10 to the 23rd, is called Avogadro's number. It's a very important number because it's telling us how many things fall into a mole. Now, basically, we're using moles to deal with numbers of things, particularly dealing with atoms, molecules, and formula units. So it's a lot of things. In fact, we could never count that many things even if we tried in our entire lifetime. But we use it for those really small things we can't see. Again, atoms, molecules, and formula units, which are representative particles. We call those representative particles of atoms for elements. Molecules go to covalent compounds. Formula units go to ionic compounds. So the reason that we talk about moles is because it's a way for us to really be able to compare things. And so when we talk about a mole of anything, it's always going to be the same number of stuff. Whether it's a mole of pencils, it's a mole of sheep, it's a mole of atoms. We're talking about 6.02 times 10 to the 23rd of those things. So it's a comparison for us to it. But one thing we find out is while we might have the same number of things, we're not going to have the same volume or the same mass of your substances. That's going to be different. Here's a couple of examples. On the left, we have a mole of water. Notice that this is 18 milliliters of water, which weighs 18 grams. But that 18 grams or 18 milliliters of water is made up of 6.02 times 10 to the 23rd molecules. Again, it's molecules because water is a covalent compound. So there's 6.02 times 10 to the 23rd molecules in this thing. Now, as we think about that, though, a little bit more, too, we can look at that because we can say, then how many atoms is that? How many atoms are in 1 mole of water? Well, if we think about 1 molecule of water is going to have made up of H2O. It's going to be made up of 2 hydrogens and 1 oxygen. So every molecule has 3 atoms in it. So if I had 2 molecules, that would be 6 atoms. If I had 10 molecules, that would be 30 atoms. If I had 100 molecules, it would be 300 atoms. If I had a mole of molecules, that will be 3 moles of atoms. 2 moles of hydrogens, 1 mole of oxygen atoms. The bottom right picture down here that we see is showing equal quantities, again, equal numbers of particles of several different substances. We have 1 mole of mercury 2 oxide, 1 mole of sucrose, a mole of copper 2 pentasulfate, sulfate pentahydrate, a mole of sulfur, sodium chloride, and copper. These are all equal number of particles. There's exactly 6.02 times 10 to the 23rd particles in each one of these. Formula units for mercury 2 oxide, molecules for sucrose, atoms for sulfur, formula units for copper 2 sulfate, formula units for sodium chloride, and atoms for copper. They're all 1 mole, but they take up different volumes and they have different masses. Now, why exactly might that be? Why might equal quantities of things have different masses? It's pretty simple. It's because, you'll see in the next slide, it's because different atoms have different sizes and masses themselves. So if I took 10 toasters and versus 10 pencils, I have exactly the same number of things, 10 pencils, 10 toasters, but the toasters are going to weigh more and take up more space because a toaster is bigger than a pencil. That's what we're looking at in this case. So moles also kind of work like this. If I have a carton of eggs, 1 carton is 12 eggs. So I can write this as 1 carton of eggs times 12 eggs in a carton is 12 eggs. What if I have 2 cartons of eggs? Okay, 2 cartons times, again, each carton has 12 eggs in it, so 12 eggs per carton is 24 eggs. The same thing is going to apply as we're dealing with moles. 10 cartons of eggs is 10 times 12 eggs per carton, or 120 eggs. Okay? So the mole thing works exactly the same thing. Since 1 mole of substance is 6.02 times 10 to the 23rd things, I can use that as a conversion factor just like I did in these previous examples. So let me switch colors here. This 6.02 times 10 to the 23rd over 1 mole is a conversion factor. It's letting us change from one unit to another. So if I take 1 mole times how many things are in a mole, which is 6.02 times 10 to the 23rd, I would get 6.02 times 10 to the 23rd things, whatever those things are going to be. Generally, though, for our purposes, it's going to be atoms forming units or molecules, but it could be anything. Cartons of eggs, pennies, dollars, whatever. And same thing, 10 moles would be times 10 times how many things are in 1 mole, or 6.02 times 10 to the 24th things in a mole. We can do exactly the same thing going backwards as well. I could say if I have 2 moles, or 2, let's go 2 times 10 to the 30th atoms, how many molecules is that? I'm still going to multiply by a conversion factor, but in this case, my atoms are my thing, so to get rid of it, that has to go on the bottom, so there's where my 6.02 times 10 to the 23rd is going to be for my conversion. And there is one, makes up 1 atom, or one, actually not 1 atom, but 1 mole. Let me switch that. So I was going to write atoms, but that was going to be wrong. And so that's going to be approximately 3 times 10 to the 7th, or 27th, because we subtract our exponents. So maybe a 26th power. But we just do that division, and that's going to be how many moles we have for our substance. Okay, so again, why? Why do these things have different masses and different volumes? Because atoms are different sizes, like we talked about with the toasters versus a pencil. I have the same number of each, but they're going to have different masses and different volumes. Okay, what are moles used for? Moles are used to count things. Chemical reactions occur because certain numbers of things react. Okay, so that's how we have to look at reactions. Reactions are based on how many things, how many atoms and molecules are coming together with each other. But since those numbers are so big, there's no way that we can actually count out how many atoms we have to be able to react with something else. We measure in lab grams. We measure mass. So we have to figure out what's the relationship between mass and moles, and also the numbers of particles. Well, very simply, we can use a little flowchart thing like we saw in your worksheets to kind of show what that is. And you can come back and pause this and get this written down as a little flowchart because it's really going to help you. So you can see, let me pull this back up a little bit for now, that if we can go from any quantity to any of the other 3 quantities here. So if I have moles and I want to know what the mass is, I have conversions here that tell me what to do. I find out what I start with, and I follow the arrow. I follow what the conversion says to do on the arrow in order to change from one unit to the next. So if I want to go from moles to grams, I'm going to do this thing, follow the arrow to get to grams, where I take the grams is equal to moles divided by something called the molar mass. If I have mass, I want to get to moles. I'm going to take moles equals the grams I was given, divided by what that molar mass was. I'm going to talk about molar mass in a second. To go from moles to particles and back and forth, to go from moles to particles, we follow the bottom arrow. We take the number of moles multiplied by Avogadro number of things per mole. And to get from particles to moles, we divide by Avogadro's number. Notice that we can't go directly from particles to mass. You can't go right from here and skip right to mass. You have to go through moles to get there. Or vice versa. If you're given a mass of a substance, to figure out how many particles there are, lights just went out, we have to be able to go to moles first. Right back. Sorry about that. Now if we pull this down a little bit more again, we'll kind of explain this again a little bit differently. We're looking at the relationships between mass, moles, and particles in this case. MM is molar mass, G is grams. Again, your particles are those representative particles of a substance. Elements are atoms, molecules for covalent compounds, and formula units for ionic compounds. So if I have moles, I'm going to take moles times the molar mass and I'll have grams. And if I have grams when I get to moles, I'm going to take the grams divided by that molar mass. And we talked about Avogadro number on the other side. Okay, now what exactly is molar mass? All molar mass means is that we have the mass in grams of 1 mole of a substance. That comes in very handy because that's a way for us to compare substances to each other. We know we have a certain amount of your substance. We have the same number of particles, same number of atoms, same number of molecules, same number of formula units. We compare the mass of that value to kind of give us some relationship ideas. So a mass of copper is going to weigh less than a mole of copper is going to have a smaller mass than a mole of gold, even though they're the same number of particles, but they're equal number of particles. And that's the important part. So molar mass has a couple of steps to be able to find it for any element or a compound. For an element, it's pretty simple. For an element, molar mass is just the atomic weight. For a compound, though, what we're going to do are these steps. We're going to write all the elements in a compound vertically. You'll see an example on the next page. We're going to write down what the atomic mass of each element is. We're going to multiply those atomic masses of each element by how many atoms are in the formula overall. And then we're going to add all those totals together, each total mass contribution of each element, and that will be your total, will be your molar mass, the mass in grams of 1 mole of a substance. So here's an example, a simple example with water, H2O. Hydrogen and oxygen are the 2 elements in it. Notice I don't put the subscripts in, I just write what all the elements that are present in our formula. I write down the atomic weight. Hydrogen is 1 gram per mole, and atomic weights we're going to round to the nearest whole number. Oxygen is 16 grams per mole. I multiply that by how many atoms are in my formula. There's 2 hydrogens, there's 1 oxygen. And that gives a total contribution from each element. So 1 times 2 is 2, 16 times 1 is 16. I add 2 and 16 together to get 18 grams per mole. And that tells me that 1 mole of water, 6.02 times 10 to the 23rd molecules of water, is going to weigh 18 grams. Okay, important number because that's what we're going to compare to other substances. Now another example on this page that we're going to kind of work through at the same time here. So again, the first thing I'm going to do is I want to find out what the atomic weights are. Atomic weight. Looking at your periodic table, nitrogen is 14 grams per mole. Hydrogen is 1 gram per mole. Phosphorus is 31 grams per mole. And oxygen is 16 grams per mole. So I write these all vertically, I write these atomic numbers in. We're going to multiply by the number of atoms in our formula. Okay. So how many nitrogens are there? There's parentheses here, there's 1 here, but 3 times 1 is 3. There are 12 hydrogens, 4 times 3 is 12. 1 phosphorus, 4 oxygens. That gives us the total contribution per element. 3 times 14 is 42 grams per mole. 12 times 1 is 12 grams per mole. 31 times 1 is 31 grams per mole. And 16 times 4 is 64 grams per mole. Now all I have to do is add these all up to find what my molar mass is. 4 and 4 is 8, plus 1 is 9. 5 and 3 is 8, plus 6 is 14. So ammonium phosphate, 1 mole of ammonium phosphate would weigh 149 grams. And we do that for any compound, any element to find its molar mass. Once we have that molar mass, then we can do those conversions between mass and moles. We just want to follow our arrows then in this case. So if I have mass, again, and I want to find out how many moles it is, I take my grams as mass times molar mass. Or actually I want to get to moles. Moles is grams divided by molar mass. So if I had 14 grams of ammonium phosphate, I would take 14 grams divided by the molar mass, which we just found was 149, and that would be how many moles I would have. Okay, if I had 6 moles of water, how many grams would it be? 6 moles times the molar mass of water, which we saw 2 slides ago, which is 18. 6 times 18 would be the mass of that many grams. And I could also change the particles then by either multiplying or dividing by Avogadro's number. Again, depending on where you start with and what you want to go to. You can go 2 steps, you can go 1 step, or we can do some other things that we'll be taking a look at tomorrow as well in our skill tests or skill activities. And that's it. That's where we end up with today. We're going to be taking a look at important things using our conversions here tomorrow. We're going to be looking at finding molar masses, finding grams, finding moles, finding how many atoms we have present before we move on into the last parts of the chapter, which are talking about empirical formulas and molecular formulas. Okay, we'll see you tomorrow in class.